Hello, everyone. I'm hoping we have people attending from all around the world. So I'm going to say good morning, good afternoon, good evening to all of you. So my name is Freda VAN WYNGAARDT. I work for the Australian Nuclear Science and Technology Organisation, ANSTO, and our team is responsible for maintaining Australia's measurement standards for radioactivity. So it is my pleasure today to be chairing this webinar on radionuclide reference materials. So as a chemist, I've always been interested in the process of producing reference materials, and my limited experience highlighted the importance of doing this well. So I really look forward to learning from Ivana today. Now, Ivana VUKANAC is a trained nuclear physicist. She studied at the University of Belgrade in Serbia, focusing on applications in environmental protection. So previously, Ivana worked at the Vinča Institute of Nuclear Sciences, that is also in Belgrade. So since October 2023, Ivana has been working at the IAEA Terrestrial Environmental Radiochemistry Laboratory in Sabersdorf in Austria. Here, Ivana is responsible for the production of reference materials and also for organizing proficiency tests and other tasks associated with their mandate. So Ivana has extensive experience in environmental monitoring, radiation protection, and also many aspects of radionuclide metrology. She has worked in ISO 17025 and ISO 17034 accredited laboratories, and she's the co-author and author of more than 50 published papers published in peer-reviewed journals. So I look forward to learning from you. So over to you, Ivana. Thank you.
This will be a presentation on radionuclide reference materials. And in summary, I will give you some information, introduction on Turk laboratory. Then we will go through some definitions of reference material, terminology related to reference material, and the role of reference material in measurement process. Then we will go through reference material production, and I will tell you a bit about reference material in Turk laboratory and about our Turk worldwide proficiency testing exercise. Well, Turk Terrestrial Environmental Radiochemistry Laboratory is one of the four environmental laboratories. It is located in the IAEA laboratories in Sabersdorf, some 40 kilometers away from Vienna. Laboratory has a long history, and since 1960s, when it was a chemistry unit, it has been growing continuously in terms of activities, expertise, and quality of performed work. Nowadays, since 2022, the name of the lab is, like I said, Terrestrial Environmental Radiochemistry Laboratory, and we are part of Division of Physical and Chemical Sciences of the Department of Nuclear Science and Application here in the agency. What is our mission? Well, the key task of Turk Laboratory is to provide expertise, training, and support to the member states dealing with radioactive, industrial, and other pollution, and to assist member states in preparing for emergencies. Turk supports the member states' laboratories in improving their measurement capabilities in environmental monitoring and in providing reliable analytical results by providing reference materials on both radionuclides and stable isotopes, and by organizing worldwide proficiency testing exercise, which is once per year. To achieve our mission, we have some measuring equipment, but besides this, we have also all necessary infrastructure needed for reference material production, storage of reference material, and their distribution. In Turk laboratory, we perform trace element analysis, stable isotope analysis, and of course radionuclide analysis. And for the purpose of measurements of radionuclides, we have well-equipped gamma spectrometry laboratory with 7 high-purity germanium detectors. We have well-established alpha spectrometry and beta spectrometry with 36 alpha detectors and 3 liquid scintillation counters. For sample preparation, we have nice radiochemistry lab, and also we have 2 gas flow proportional counters for measurement of gross alpha and gross beta activity. Let us see now what are the reference material and how they can be used, how they are used. In preparation of this presentation, I found that there are many publications that mention reference materials, giving the definitions and other information and terminology regarding reference material and reference material production. Here I will present several internationally recognized documents, such as ISO standards and guides, but also BIPM's International Vocabulary of Metrology. What we will see from these documents, the definitions are not so different, so documents are well harmonized. And in the next few slides, I will give you, in summary, not word to word, the relevant definition and terminology. Let us start with ISO 17034. This is a standard giving requirements for competence of reference material producer. So, reference material is material sufficiently homogeneous and stable with respect to one or more specified properties. Certified reference material is reference material characterized by a metrologically valid procedure for one or more specified properties, accompanied by a reference material certificate that provides certified values, value of a specific property and its associated uncertainty, and statement of metrological traceability. If we speak of radionuclides reference material, specified property or analyte is radionuclide activity per unit mass or per volume unit. In the International Vocabulary of Metrology, we have basically the same definitions, but with some addition of very useful notes saying that reference material can be used for measurement precision evaluation. It can be used for calibration, but for that it needs to be certified reference material, and also for assessing measurement trueness. A given reference material can only be used for one purpose in a measurement process, either for calibration or for quality control purposes, but not the both at the same time. Besides these definitions, I would like to give one more of the term which is very important, not just for reference materials, but also for any laboratory dealing with radioactivity testing and providing the results to a customer, and this is metrological traceability. It is a property of measurement results whereby the result can be related to a reference through a documented, unbroken chain of calibration, each contributing to the measurement uncertainty. Vocabulary gives, again, useful notes, and here I included some of them. For example, the second one, for measurements with more than one input quantity in the measurement model, each of the input values and their uncertainties should itself be metrologically traceable. Again, if we speak about measurement of radionuclide concentration, we give results in becquerel per kilogram or volume unit, which means that the result is metrologically traceable if we can document the unbroken chain of calibration for the measured mass or volume and measured activity for the becquerel. For the usage of reference material, ISO 17034 says that reference material are used in all stages of measurement process, including for method validation, calibration, and quality control. Reference material are also used in interlaboratory comparisons for method validation and for assessing laboratory proficiency. So this is quite general, and how reference material should be used is given in more details in another ISO standard, 17025, which gives the general requirements for the competence of testing and calibration laboratory. This is a kind of normative reference in ISO 17034, and I believe that many of you are familiar with this standard. In the standard, clause 6 defines resource requirements, saying that our equipment shall be calibrated, that metrological traceability of measurement results shall be maintained, that measurement results shall be traceable to the international system of units through, for example, certified values of certified reference materials provided by a competent reference material producer with stated metrological traceability to the SI. Here, competent reference material producer is the one fulfilling the requirements of ISO 17034. For example, radionuclide reference materials, agency ones, IAEA radionuclide reference material, are traceable for the mass. Results is traceable to the national standard through external calibration of balances, and for the activity, result is traceable to the certain national standard of activity of radionuclide, which depends on the radioactive solution that we used for efficiency calibration of our gamma spectrometers. So let's say a few words about calibration. In laboratories where radioactivity needs to be determined by relative methods like gamma spectrometry is, measuring system needs to be calibrated, and proper calibration will ensure a reliable result, but also will ensure the traceability of the measurement results. In gamma spectrometry, we have several approaches for calibration, and depending on the standard or reference material we use for that, our results is traceable to a level stated in the certificate of that standard or certified reference material. Further, in clause 7, we have requirements regarding the process, saying explicitly how and where reference materials could and should be used. So, to summarize, reference material could be used in all stages of measurement process, including calibration and different QA/QC activities. If we have in mind the importance of reference material in all stages of measurement process, the quality of produced reference material is of crucial importance for obtaining the good, reliable measurement results. As I said earlier, requirements for reference material producers are given in ISO 17034, and in the next part of the presentation, I will go through the provisions of this standard describing the process of reference material production. I mentioned already, Turk Laboratory is accredited reference material producer since 2022. And the scope of our accreditation is production of matrix certified reference materials characterized for activity concentration of gamma ray emitting radionuclides. This production is supported by 3 analytical techniques: gamma ray spectrometry, particle size analysis, and dry weight determination. Purpose of the accreditation is to ensure consistent quality of produced reference materials and to achieve international harmonization through compliance with standard requirements. To support reference material production, we have a well-established quality management system, and to achieve international harmonization of reference material production, and to achieve international harmonization, reference material production is in line with the requirements of ISO 17034. Like any standard, this one is consisting of numerous requirements, but here I will focus on clause 7, which gives technical and production requirements for reference material production. On this slide, you can see an overview of clause 7. There are 18 sub-clauses covering all technical aspects of reference material production, and I will focus mainly on these in dark blue. So let us start from the beginning. Like in any activity, good planning is important prerequisite for the success. In a planning phase, all aspects of project should be considered, starting with the specification and acquisition of the material, processing, packing, then stability and homogeneity assessment. It is followed, or at the same time, by characterization of the material. And then after the characterization, we do value assignment and uncertainty assessment. After the preparation of reference material documents, adequate post-release monitoring scheme needs to be followed. So all what was mentioned needs to be documented. Like ISO said, if it is not recorded, it didn't happen. We do it in a reference material project planning form. I gave you our, as an example, our reference material project planning form. It needs to cover all processes which directly affect quality of reference material, like, I don't know, environmental conditions, characterization campaign, stability testing, everything. In total, 21 items needs to be addressed in this recording. In line with subclause 7.4, material handling and storage shall ensure integrity of candidate reference material through production process. Also, we need to have adequate packing and labeling, then appropriate storage location under the control environmental conditions, and we need to do assessment of condition of reference material at appropriate intervals throughout storage period. Before subclause 7.5 is about material processing, but before processing the material, during the planning phase, a feasibility study should be conducted in order to assess whether the sampled material is even suitable candidate for reference material. This means to roughly estimate radionuclide content of the material, levels of radioactivity, and so on. but also this is a time when decision needs to be made if the material is going to be spiked or not. Processing after that, if we find that it is a suitable candidate, then we process the material. Processing like processing is just usual one: drying, milling, sieving, homogenization with the bulk homogeneity assessment following. Then stabilization, we do that by sterilization by irradiation, and finally packing or bottling the reference material in units. Next clauses, subclauses 7.6 and 7.7 are about the requirements for measurement procedures and equipment to be used in reference material production process. Basically, they say that measurement procedures and equipment maintenance shall be in accordance with ISO 17025. Provision of these standards was mentioned before, and I would not go into details here. Next one, subclause 7.8 is about data integrity and evaluation. To meet this requirement, security of the data shall be guaranteed. Then calculations and data transfer needs to be checked. In Turk laboratory, we have implemented so-called 4I principle, meaning that each data transfer or calculation needs to be verified or checked by another person. Spreadsheets that we use as a part of QMS documents are locked, password protected and validated, and software used as well. One of the most important features of the reference material is homogeneity. I mentioned before that bulk homogeneity assessment will tell us if the material is ready for final bottling. But after bottling, comprehensive homogeneity study needs to be done. Subclause 7.10 of ISO 17034 give us requirements like that assessment of homogeneity is performed either by prior evidence or by experimental assessment, which is in most cases necessary. Standard says that assessment of homogeneity needs to be done with the reference material in its final packed form. Then that homogeneity needs to be assessed for every property of interest, meaning that if we are planning to certify, let's say, lead-210 and cesium-137, then homogeneity needs to be assessed for each radionuclide. Then we need to measure a representative number of randomly selected units. Detailed description and recommendations how to do this homogeneity assessment are given in the ISO 33405, which gives guidance for homogeneity, stability assessment, and for characterization. This standard distinguish, it says that we need to use validated measurement procedures, and it distinguish between unit and within unit homogeneity. Between unit homogeneity is assessed to ensure that all units are equal, and within unit to ensure uniformity when using some samples from one unit. Within unit homogeneity is reflected directly in minimal size of a subsample that is representative for the whole unit. That's how we determine minimum sample intake by the method for which we guarantee homogeneity of the reference material. As a result of homogeneity study, we obtain uncertainty contributor from heterogeneity of the material in the uncertainty budget, or we declare that it is negligible. For radionuclide matrix, radionuclide reference material, this contribution is about 3 or 5, up to 5%. Stability of assigned property value is another very important characteristic of reference material. It is covered with subclause 711 of ISO standard 17034, and this standard recognizes two types, let's say like this, of stability assessment before and after the reference material is released. Before release, so-called short-term or transport stability needs to be assessed. This is done under the simulated extreme transport conditions. Also, stability of reference material during the production process is assessed, and this is under the storage condition, and this is something that we call long-term stability. Again, experimental design, detailed descriptions and recommendations how these studies should be done are given in ISO 33405. And then, based on the results of stability studies, we can estimate the uncertainty of certified value due to instability, or say that this is that it is negligible. Then we can predict shelf life of reference material, assign appropriate period of validity, and to make a monitoring scheme after the release to detect any changes in a timely manner for the specific reference material. And also we use these results as a part of instruction for users of reference material. After the release of reference material, long-term stability monitoring needs to be done during the shelf life of reference material according to previously mentioned established scheme. So control measurements are performed regularly. It is usually once per year or once per 2 years, and results are used to confirm certified values and or for extension of the validity of reference material. Next step in reference material production is characterization. Characterization of reference material is about determination of property value, determination of associated uncertainty, and it's about providing evidence of the metrological traceability of assigned value. Again, general requirements are covered with subclause 712 of 17034, and practical guidance are given in ISO 33405. Here on this slide you have some recommendations for appropriate characterization strategy. In Turk, we mostly used characterization based on the mass of added activity during the preparation of reference material, so-called spiking, or we did characterization using the results obtained from number of competent laboratories. Whatever approach is chosen, characterization strategy needs to be well planned. Competence of involved laboratories should be demonstrated, and if the characterization is performed by obtaining results from more laboratories, technical evaluation of received data must be done. The last phase in, let's say, physical production of reference material is assignment of property value and its uncertainty. How we do it? It's directly connected with the choice of characterization strategy. Like I said before, in Turk we usually choose two types of strategy and perform value assignment by formulation for spike materials or using the network of expert laboratory. So whichever approach is used in value assignment, description of experimental design and statistical techniques used needs to be provided. Also, the policies of treatment of anomalous results, outliers, needs to be, policies needs to be said and described in planning. In value assignment, we need to consider all available technical information, including reported uncertainty and evidence of laboratory performance. Statistical techniques used in value assignment strongly depends on study design and quality of obtained data set, meaning what is the number of data points, are individual points independent, and if uncertainties of individual data points are comparable. ISO 33405 gives us some recommendations on statistical approaches that could be used in value assignment. And last but not the least, after performing stability study, homogeneity study, and characterization, we have all information necessary and we combine all obtained contributors and form comprehensive uncertainty budget for the assigned value. Now we are going to, let's say, administrative work, since the certified reference material is not complete without the reference material documents. What are these documents? First, First, it is the certificate containing all relevant information on certified reference material, including assigned value with associated uncertainty and statement of metrological traceability. Also, non-certified reference material can come with a reference sheet on similarly called document, which contain information essential to the use of reference material. And also, although it is not requirement of the standard, some certified reference material comes with a certification report where you can find all the information about the material and in addition about the production process. For example, on our reference material web page, you can find, let's say, three categories: reference material under ISO accreditation, certified reference material, and reference material. Here I put some examples. For the first two, we have certificate, which contain value for activity concentration, associated uncertainties, and statement of metrological traceability, but also information on its intended use, origin of the material, homogeneity and stability assessment, dry weight determination, and instruction for use. For the reference material, we have reference sheets, which does not contain all of this information. In line with ISO 17034, IAEA Reference Material Certification Committee, RMCC, is established. it is certification panel formed to overview all aspects of reference material production. RMCC approves certified or information values. It is formed to approve release of IAEA reference materials and to ensure that reference materials comply with ISO standards and related internal QMS documents. RMCC assigned the selling price for the reference material, and it also check and revise the status of reference material over the material lifetime. Nearing the end of my presentation, I would like to give you some information of reference material production here in Turk. Like I said, laboratory has a very long tradition in reference material production, and as you probably know, IAEA is a world major supplier worldwide for reference materials for stable isotopes and natural matrix radionuclide reference materials. And what I want to emphasize here is that Turk laboratory holds the primary reference materials for hydrogen, carbon, oxygen, nitrogen, and sulfur stable isotopes ratio. On the right-hand side on the slide, you can see one material which is currently under the preparation. So, what I presented and what you could see from this presentation is that the production of reference materials is demanding and ongoing task, and this task is not ended with the release of reference material. Well, especially if you have in mind the scale of production and quantity of produced units. IAEA reference materials are usually produced in batches of several hundreds, like 400 or 500 units. So big portion of our working time is devoted to activities related to reference materials, starting with the planning and what is visible from the end user side, maintaining the web shop for reference materials. Here I gave you on this slide link to our web shop, and now we have approximately 100 reference materials available. Approximately quarter is for matrix radionuclides reference material, and we provide approximately 2,000 reference material units to over 600 customers from approximately 80 countries every year. And also, as I said in the beginning, I would like to give you some information about Turk's worldwide proficiency testing exercise. It is activity which support member state laboratory in improving their measurement capabilities in environmental monitoring and in providing reliable analytical results. This is one of the first services to member states since the IAEA had been established. It was called intercomparisons, and in early 1960s it was about gross alpha and gross beta activity and determination of strontium 90, and somehow it was designed for value assignment of reference material. So it has been always connected with reference material production. Nowadays, in our proficiency testing exercise, we have gamma ray emitting radionuclides, measurements of beta and alpha emitting radionuclides, natural and artificial ones. Then we have printed surfaces, trace element analysis in samples like water and matrix environmental samples. Based on results from the PT, we do some gap analysis, and usually after the PT, we have some trainings or webinars covering the challenges that have been identified in results of PT. Each year we have increase of the number of participants. In 2024, we had more than 500 laboratories. So this service is free of charge, and PT can be ordered in the link given in this slide. Here you can see some typical sample sets sent to the PT participants on this slide. And finally, I was thinking what can be the conclusion of this presentation, and on this slide I have listed a few points that I would like to leave with you after this webinar. First, to remember that reference material play an important role in measurement process, that they are used in all stages of measurement process, including for method validation, for verification. They can be used for calibration, quality control, and quality assurance. The quality of reference material used in the analytical laboratory directly reflects on the quality of the obtained results. Then, high quality of reference materials is ensured through compliance of reference material production process with relevant standards and recommendations. Certified reference material must meet high requirements regarding homogeneity and stability, as well as the uncertainty and traceability of certified values. And in summary, usage of reference materials contributes to ensuring accurate and reliable results for environmental radioactivity measurements, providing a basis for informed decision-making in management of environmental contamination, for example, or to ensure the safety of food and drinking water. With this, I would conclude my presentation. We have one more slide where I listed the references used, and one more where I say thank you for your attention and thank you for joining this webinar.